Our universe holds secrets, mysteries that defy our everyday experiences. What if I told you there are dimensions beyond what we can see and touch? Dimensions hidden from our perception, yet possibly all around us. This is the realm of hidden dimensions, a place where the very fabric of reality twists and turns in ways we are only beginning to comprehend. For centuries we've lived in a world defined by length, width and height. Time, the fourth dimension, dictates the flow of events. But what if these familiar dimensions are just the tip of a cosmic iceberg? What if there are more hidden dimensions, curled up so small that they remain invisible? The quest to unravel this enigma has captivated scientists and dreamers alike. It's a journey into the heart of existence, a quest to understand the very nature of the cosmos. Join us as we delve into the mind-boggling world of hidden dimensions, where the impossible might just be possible. Imagine a tightrope walker gracefully moving across a high wire. From our perspective, they exist in a one-dimensional world, able to move only forward or backward. But what if there are other dimensions unseen by us that the tightrope walker can access? Our senses are limited, attuned only to the familiar three spatial dimensions. We perceive the world as a flat canvas, unaware of the potential depths hidden from view. But just as the tightrope walker can move in ways we might not immediately grasp, so too might there be dimensions beyond our perception. This is the tantalizing possibility that has ignited the imaginations of physicists and mathematicians. Could there be a reality beyond our senses? A reality where the laws of physics operate in ways we can barely imagine? The search for hidden dimensions is a journey into the unknown. It's a quest driven by curiosity, a desire to peer beyond the veil of our everyday experience. And while the concept might seem like something out of science fiction, the evidence for hidden dimensions lies in the very fabric of our universe. From the smallest subatomic particles to the largest structures in the cosmos, there are hints that our universe is far more complex than it appears. The way gravity behaves, the strange interactions of quantum particles, these phenomena suggest that there might be more to reality than meets the eye. Table of Contents, Part 2, Act 1, about 8 sections. 1. The building blocks of reality. 2. Navigating our 3D world. 3. The curious case of time. 4. Beyond the familiar. 5. The realm of the extra dimension. 6. Unraveling the fabric of space-time. 7. The quest for a unified theory. 8. Clues from the quantum realm. To understand hidden dimensions, we first need to grasp the dimensions we experience every day. Our world is built upon three spatial dimensions: length, width and height. Think of a cube. It has length extending from one side to the other, it has width spreading out across its base, and it has height rising up from its foundation. These three dimensions define the space we live in, allowing objects to exist and move within it. Every object we encounter, from a tiny grain of sand to a towering skyscraper, can be described using these three dimensions. They are the fundamental building blocks of our spatial awareness, the framework upon which our reality is constructed. Imagine yourself standing at a specific point. To describe your location, you need three coordinates: your position along the length axis, your position along the width axis, and your position along the height axis. These three coordinates pinpoint your exact location within the three-dimensional space. Now imagine you want to move. You can move forward or backward along the length axis, left or right along the width axis, or up or down along the height axis. Every movement you make can be broken down into these three fundamental directions. These three dimensions are not just abstract concepts, they are woven into the very fabric of our existence, shaping our perception of the world and dictating how objects interact with one another. But there's more to our reality than just spatial dimensions. We also experience time, the relentless flow from past to present to future. Time is often considered the fourth dimension, adding another layer to our understanding of the universe. Unlike the spatial dimensions, we can't move freely through time. We are swept along its current, unable to rewind or fast forward at will. Yet time is essential for our existence, governing the sequence of events and giving order to the chaos of the cosmos. While we can move through space in any direction, we experience time as a one-way street, always moving forward. This unique property of time sets it apart from the spatial dimensions and has profound implications for our understanding of reality. So far, we've explored the familiar dimensions that shape our everyday experiences. But what if these four dimensions are not the whole story? What if there are hidden dimensions beyond our perception that hold the key to unlocking the universe's deepest secrets? The idea of hidden dimensions might seem like something out of science fiction, but it's a concept that has captivated physicists and mathematicians for decades. The quest to find these hidden dimensions is a journey into the unknown, a search for the hidden structure of reality itself. To understand how these hidden dimensions might work, we need to stretch our imaginations and consider possibilities that defy our everyday intuitions. Imagine a tightrope walker gracefully moving across a high wire. From our perspective, they exist in a one-dimensional world, able to move only forward or backward along the rope. But what if there are other dimensions, unseen by us, that the tightrope walker can access? These hidden dimensions might be curled up so small that they are invisible to our eyes and even our most powerful instruments. Yet just as the tightrope walker can move in ways we might not immediately grasp, so too might there be particles and forces operating in these hidden dimensions, influencing our reality in subtle but profound ways. The concept of hidden dimensions is not merely a mathematical curiosity, it's a tantalizing possibility that could revolutionize our understanding of the universe and our place within it. To visualize these hidden dimensions, imagine the fabric of space-time as a smooth sheet. Now, picture tiny, curled-up dimensions attached to every point on that sheet, like minuscule loops too small to see with the naked eye. These loops represent the extra dimensions, hidden from our view because they are curled up at an incredibly small scale, far smaller than anything we can currently observe. While we experience the smooth sheet as our familiar four-dimensional universe, these hidden dimensions could be teeming with activity, influencing the behavior of particles and forces in ways we are only beginning to comprehend. The idea of hidden dimensions, curled up and hidden from our view, might seem strange at first, but it's a concept that emerges naturally from some of the most advanced theories in physics, such as string theory. One of the biggest mysteries in physics is the incompatibility between Einstein's theory of general relativity, which describes gravity on a large scale, and quantum mechanics, which governs the behavior of particles on an incredibly small scale. These two pillars of modern physics seem to contradict each other, suggesting that our understanding of the universe is incomplete. This is where the concept of hidden dimensions comes into play. Some physicists believe that by introducing extra dimensions, we might be able to unify these seemingly disparate theories and develop a single, elegant framework that explains the workings of the universe at all scales. The search for a unified theory is one of the most ambitious endeavors in modern science, and the possibility of hidden dimensions playing a crucial role in this quest is both exciting and daunting. While we haven't directly observed hidden dimensions, there are tantalizing hints from the quantum realm that suggest their existence. For example, the strange behavior of subatomic particles, such as their ability to exist in multiple states simultaneously, could be explained if these particles are vibrating in hidden dimensions, with their vibrations influencing their properties in our observable dimensions. Furthermore, the weakness of gravity compared to the other fundamental forces could be because its influence is spread out not only in our familiar three spatial dimensions, but also in hidden dimensions, diluting its strength in our observable universe. The quantum realm, with its bizarre and often counterintuitive phenomena, might hold the key to unlocking the secrets of hidden dimensions and revealing a reality far more complex and interconnected than we ever imagined. The idea of hidden dimensions might seem like a modern concept, but its roots can be traced back to ancient philosophers who pondered the nature of reality. The Greek philosopher Plato, for example, imagined a world of perfect, unchanging forms existing beyond our sensory experience, a realm that could be seen as a precursor to the concept of hidden dimensions. Similarly, Hindu and Buddhist cosmology have long incorporated the idea of multiple dimensions and realms of existence beyond our own. These ancient ideas, while often shrouded in mythology and allegory, demonstrate a timeless human fascination with the possibility of hidden realities. While these early musings were largely philosophical, they laid the groundwork for later scientific inquiries into the nature of space and time, eventually leading to the development of theories that could accommodate the existence of hidden dimensions. In the 19th century, mathematicians began to explore the concept of higher dimensions in a more rigorous way. Bernhard Riemann, a German mathematician, developed the foundations of Riemannian geometry, which allowed mathematicians to describe spaces with any number of dimensions, not just the familiar three. This breakthrough in mathematics opened up new avenues for exploring the nature of space and time. Physicists, inspired by Riemann's work, began to wonder if these higher dimensions, while invisible to our senses, could play a role in the physical world. This period marked a turning point in our understanding of dimensions, shifting the focus from philosophical speculation to a more concrete mathematical framework that could be used to describe and explore the possibility of hidden realities. Albert Einstein's theory of general relativity, published in 1915, revolutionized our understanding of gravity. Einstein showed that gravity is not a force acting at a distance, but rather a curvature of space-time caused by the presence of mass and energy. Einstein's theory was a triumph, explaining the motions of planets and stars with remarkable accuracy. However, Einstein himself was aware that his theory was incomplete. It could not explain the behavior of gravity at the quantum level, the realm of atoms and subatomic particles. This incompatibility between general relativity and quantum mechanics suggested that our understanding of the universe was still incomplete and hinted at the possibility of hidden dimensions playing a role in bridging this gap. In the 1920s, physicists Theodor Kaluza and Oscar Klein independently proposed a daring idea. What if Einstein's equations of general relativity were extended to include an extra fifth dimension? They found that by doing so, they could unify gravity with electromagnetism, the force responsible for light and electricity. This unification was a major breakthrough, suggesting that hidden dimensions could hold the key to unifying the fundamental forces of nature. However, Kaluza-Klein theory had a major drawback. It predicted the existence of a particle that was never observed. Despite its shortcomings, Kaluza-Klein theory paved the way for later attempts to unify the forces of nature using extra dimensions, inspiring physicists to continue searching for a more complete and consistent theory. In the late 20th century, a new theory emerged that promised to revolutionize our understanding of the universe: string theory. According to string theory, the fundamental building blocks of matter are not point-like particles, but rather tiny vibrating strings. Just as the strings on a violin can vibrate at different frequencies to produce different musical notes, the strings in string theory can vibrate in different modes to give rise to the different particles we observe. What's more, string theory requires the existence of extra dimensions, 6 or 7 of them in fact, in order for its equations to make sense. These extra dimensions, according to string theory, are curled up at an incredibly small scale, far smaller than anything we can currently observe. Yet they have a profound impact on the behavior of strings and consequently on the nature of our universe. One of the most appealing aspects of string theory is its elegance. It provides a single unified framework for understanding all the fundamental forces of nature, including gravity, which has long resisted unification with the other forces. Moreover, string theory naturally incorporates the concept of supersymmetry, a theoretical extension of the standard model of particle physics that predicts the existence of partner particles for all known particles. Supersymmetry could help solve some of the outstanding mysteries in physics, such as the hierarchy problem, which asks why the Higgs boson, the particle responsible for giving mass to other particles, is so much lighter than expected. While string theory is still a work in progress, its potential to provide a complete and consistent description of the universe has captivated the imaginations of many physicists. As physicists delved deeper into string theory, they realized that there wasn't just one string theory, but rather 5 different versions, each with its own set of strengths and weaknesses. This realization led to a period of confusion and debate within the physics community. However, in the mid-1990s, a remarkable discovery emerged. These 5 seemingly different string theories were actually different facets of a single, more fundamental theory, dubbed M theory. M theory suggests that our universe is not alone, but rather one of many universes floating in a higher dimensional space called the multiverse. This mind-boggling concept, if true, would have profound implications for our understanding of the nature of reality itself. While the concept of hidden dimensions is theoretically compelling, the ultimate test of any scientific theory is experimental verification. So far, we haven't directly observed hidden dimensions, but there are ongoing experiments that could provide evidence for their existence. One promising avenue is to search for deviations from Newton's law of gravity at very small scales. If gravity is indeed leaking into hidden dimensions, its strength should deviate from what we expect at extremely short distances. Experiments at the Large Hadron Collider are also searching for evidence of particles that could be traveling through hidden dimensions, leaving behind telltale signatures in the debris of particle collisions. The search for hidden dimensions is a challenging but exhilarating endeavor, pushing the boundaries of our understanding and offering a glimpse into a realm where the very fabric of reality might be far stranger and more wondrous than we ever imagined. Imagine a world beyond our senses, a realm where the very fabric of reality is woven from threads of energy vibrating in dimensions unseen. This is the world envisioned by string theory, a world where the fundamental constituents of the universe are not point-like particles, but tiny, one-dimensional strings. These strings, far smaller than anything our most powerful microscopes can detect, dance and vibrate in a space-time tapestry of 10 or even 11 dimensions. Their intricate movements, governed by the laws of quantum mechanics, give rise to the particles and forces we observe, shaping the universe as we know it. Just as the strings on a cello can produce a multitude of musical notes, depending on their vibrations, The strings in string theory can vibrate in different modes, each mode corresponding to a different type of particle. This elegant concept has the potential to unify all the forces of nature, including gravity, into a single harmonious framework. In the realm of string theory, our universe is not alone. It is but one membrane, or brane for short, floating in a higher dimensional space known as the bulk. Imagine our universe as a vast sheet, a cosmic membrane, adrift in a sea of extra dimensions. These extra dimensions, curled up and hidden from our perception, could hold the key to understanding some of the most profound mysteries of the cosmos, from the weakness of gravity to the nature of dark matter and dark energy. The interactions between our brain and other brains in the bulk, mediated by strings and gravity, could have profound implications for the evolution and fate of our universe. Perhaps collisions between brains could even give rise to events like the Big Bang, the explosive birth of our universe. String theory, with its elegant mathematical framework and mind-boggling implications, has captivated the imaginations of physicists for decades. It offers a glimpse into a realm where the very essence of reality is a symphony of strings, their harmonious vibrations creating the particles, forces, and even the fabric of space-time itself. The mathematics of string theory is incredibly complex, but at its heart lies a simple and beautiful idea that everything in the universe, from the smallest subatomic particle to the largest galaxy, is connected by these fundamental strings. Their vibrations, like the notes of a cosmic orchestra, determine the properties of everything we observe, from the mass of an electron to the strength of the gravitational force. One of the most intriguing aspects of string theory is its potential to bridge the gap between quantum mechanics, the theory of the very small, and general relativity, Einstein's theory of gravity. These two pillars of modern physics have long stood in stark contrast, their principles seemingly incompatible. Quantum mechanics describes a world of uncertainty and probability where particles can exist in multiple states simultaneously. General relativity, on the other hand, paints a picture of a smooth, continuous space-time, warped and curved by the presence of mass and energy. String theory attempts to reconcile these seemingly disparate views by proposing that both quantum mechanics and general relativity are approximations of a more fundamental theory that governs the behavior of strings in higher dimensions. While direct observation of these hidden dimensions remains a formidable challenge, scientists are exploring indirect ways to detect their presence. One promising avenue is to search for subtle imprints or echoes of these extra dimensions in the cosmic microwave background, CMB radiation. The CMB is a faint afterglow of the Big Bang, a relic of the early universe that carries information about its infancy. Scientists believe that if extra dimensions exist, they would have left a distinct signature on the CMB, like ripples on a pond caused by a pebble dropped into the water. By analyzing the patterns and fluctuations in the CMB with ever-increasing precision, scientists hope to find these telltale signs, providing indirect evidence for the existence of hidden dimensions. The concept of hidden dimensions challenges our everyday intuition about space and distance. Imagine two ants crawling on a piece of paper. To them, the paper appears as a flat, two-dimensional surface. They can move forward, backward, left or right, but are unaware of the third dimension, height. Now imagine crumpling the paper without tearing it. The ants, confined to the paper's surface, would perceive their world as distorted. Their paths, once straight, would now appear curved and convoluted. They might even encounter each other unexpectedly, as if by magic, as the crumpled paper brings distant points closer together. Similarly, if our universe has extra dimensions curled up at a subatomic scale, we might be unaware of the true distances between objects. What we perceive as vast cosmic distances might be illusions, with shortcuts and hidden pathways existing in these higher dimensions. The idea of hidden dimensions opens up a universe of possibilities, challenging our assumptions about the nature of reality and our place within it. If extra dimensions exist, they could harbor unseen particles and forces that interact with our world in subtle but profound ways. Perhaps dark matter, the elusive substance that makes up a significant portion of the universe's mass, resides in these hidden dimensions, its gravitational influence felt but its true nature concealed from our view. Or perhaps dark energy, the mysterious force driving the accelerated expansion of the universe, originates from interactions with these extra dimensions. The possibilities are as vast and varied as the extra dimensions themselves, limited only by our imagination and our ability to devise experiments capable of testing these mind-boggling concepts. The search for hidden dimensions is not merely an intellectual exercise or a quest for exotic particles. It is driven by a deep desire to unify the fundamental forces of nature, to find a single, elegant framework that explains the workings of the universe at all scales. For centuries, physicists have sought to unify gravity, electromagnetism, the weak force and the strong force, the four fundamental forces that govern the interactions of matter and energy. String theory, with its requirement for extra dimensions, offers a tantalizing path towards this unification, suggesting that these forces are different manifestations of a single, underlying force. If successful, this unification would revolutionize our understanding of the universe, potentially unlocking profound insights into the nature of space, time, and the very essence of reality itself. In the grand tapestry of the cosmos, hidden dimensions might play the role of unseen architects, shaping the evolution of galaxies, the formation of stars, and even the emergence of life itself. Their influence, while subtle and often invisible, could be the guiding hand behind the intricate structures and processes we observe. Perhaps the distribution of dark matter, which is thought to provide the gravitational scaffolding for galaxies, is determined by the geometry of these extra dimensions. Or perhaps the rate of star formation is influenced by the leakage of energy or particles from these hidden realms. The interplay between our familiar four-dimensional universe and the realm of hidden dimensions could hold the key to understanding the grand cosmic drama that has unfolded over billions of years. The search for hidden dimensions is a journey into the unknown, a testament to the boundless curiosity and ingenuity of the human spirit. While direct evidence remains elusive, the pursuit of this profound concept has already yielded remarkable insights and pushed the boundaries of theoretical physics. As technology advances and our understanding of the universe deepens, we can expect even more creative and sophisticated experiments designed to probe the nature of these hidden realms. From powerful particle accelerators like the Large Hadron Collider to space-based telescopes searching for subtle anomalies in the cosmic microwave background, the quest to unravel the mysteries of hidden dimensions will continue to inspire and challenge generations to come. Understanding hidden dimensions can be challenging, but real-life analogies can make this abstract concept more tangible. Consider a garden hose. When viewed from a distance, it appears as a one-dimensional line. However, upon closer inspection, it's clear that the hose has a circular cross-section, a hidden dimension that wasn't apparent from afar. Similarly, our perception of the universe might be limited. Hidden dimensions could be tightly curled up at such a small scale that they elude our everyday experience. Imagine if those extra dimensions were wrapped so minutely that they only reveal their influence under extreme conditions, like in the heart of a black hole or at the moment of the Big Bang. This analogy helps to illustrate how hidden dimensions might exist all around us, influencing the physical laws and particles we observe without being directly visible. Just as we need a closer look to see the full structure of the hose, we need advanced tools and theories to glimpse these hidden dimensions. By thinking in these terms, we can begin to appreciate the complexity and subtlety of the universe, which may contain far more than meets the eye. Analogies like these serve as bridges connecting our familiar experiences to the mind-bending concepts of modern physics. Advances in technology have always been crucial in expanding our understanding of the universe. When it comes to hidden dimensions, cutting-edge technology plays an even more vital role. Consider the telescope, which opened up the cosmos to human eyes, or the microscope, which revealed the world of the very small. Today's physicists rely on particle accelerators, advanced sensors, and highly sophisticated computer models to hunt for evidence of hidden dimensions. These tools allow scientists to probe deeper into the fabric of reality, looking for tiny anomalies and patterns that might hint at the existence of extra dimensions. For example, the Large Hadron Collider at CERN smashes particles together at tremendous speeds, recreating conditions similar to those just after the Big Bang. By analyzing the resulting particle debris, scientists hope to find deviations from known physical laws that could indicate the presence of hidden dimensions. These technological advancements are like the new lenses through which we can view the universe, revealing aspects of reality that were previously hidden from us. As our tools improve, so too does our ability to test and explore the theoretical predictions of hidden dimensions. Particle physics offers some of the most promising avenues for detecting hidden dimensions. Experiments at facilities like the Large Hadron Collider, or LHC, are designed to look for evidence that particles can move into or interact with hidden dimensions. One of the key phenomena that physicists investigate is the behavior of gravitons, hypothetical particles that mediate the force of gravity. If gravitons could move into extra dimensions, they might be detectable as missing energy in particle collision experiments. This would suggest that some of the energy from these collisions is being carried away into dimensions beyond our three-dimensional space. Another approach is to study the properties of known particles, such as electrons and neutrinos, under extreme conditions. Any unusual behavior might hint at interactions with hidden dimensions. For instance, if particles exhibit unexpected mass or decay patterns, it could be a sign that extra dimensions are influencing their properties. The results from these experiments are carefully analyzed and compared with theoretical predictions. Even a small anomaly can provide a significant clue, potentially leading to groundbreaking discoveries about the fundamental nature of reality. Gravitational waves, ripples in the fabric of space-time caused by massive cosmic events, offer another potential window into hidden dimensions. Detected for the first time in 2015, these waves provide a new way to probe the universe. If hidden dimensions exist, they could affect the propagation of gravitational waves. By studying the characteristics of these waves as they travel through space, scientists can look for subtle deviations from the expected patterns predicted by general relativity. Such deviations might indicate interactions with extra dimensions. The advanced detectors used in these studies, such as LIGO and Virgo, are incredibly sensitive, capable of measuring distortions in space-time smaller than a proton. As our detection capabilities improve, the data gathered from gravitational waves could provide crucial insights into the structure of the universe and the possible existence of hidden dimensions. These observations represent a new frontier in the search for hidden dimensions, complementing the work done in particle physics and helping to build a more comprehensive understanding of the cosmos. The large-scale structure of the universe, including galaxies, clusters, and the cosmic web, might also hold clues to the existence of hidden dimensions. The way matter is distributed and the gravitational interactions on these scales could be influenced by extra dimensions. Theoretical models suggest that hidden dimensions could impact the behavior of dark matter, an invisible substance that makes up most of the universe's mass. If dark matter interacts with hidden dimensions, it might explain some of the anomalies observed in the rotation curves of galaxies and the movement of galaxy clusters. Additionally, the formation and evolution of cosmic structures could be influenced by the geometry of hidden dimensions. For instance, if extra dimensions affect the gravitational force, they could alter the way galaxies cluster together and the overall dynamics of the universe. By comparing observational data with theoretical predictions, scientists can look for patterns that might suggest the presence of hidden dimensions. This approach requires sophisticated simulations and detailed analysis, but it has the potential to reveal new facets of the cosmos and the underlying principles that govern its behavior. Dark matter and dark energy are two of the most mysterious components of the universe, and, well, they might be connected to hidden dimensions. Dark matter, which does not emit or absorb light, interacts gravitationally with visible matter and influences the structure of the universe. One hypothesis is that dark matter could be particles that interact with hidden dimensions. These particles might move through extra dimensions, affecting their behavior and making them difficult to detect directly. This could explain why dark matter only interacts via gravity and not through the other fundamental forces. Dark energy, which drives the accelerated expansion of the universe, might also have links to hidden dimensions. If the extra dimensions have specific properties or dynamics, they could influence the energy density of the vacuum and lead to the observed acceleration. By studying the properties and effects of dark matter and dark energy, scientists hope to uncover hints about hidden dimensions. These investigations could provide a deeper understanding of the universe's composition and the fundamental forces at play. The Large Hadron Collider at CERN is one of the most powerful tools in the search for hidden dimensions. By colliding protons at nearly the speed of light, the LHC recreates conditions similar to those just after the Big Bang, allowing scientists to explore fundamental questions about the nature of reality. One of the primary goals of the LHC experiments is to search for evidence of particles escaping into hidden dimensions. If such particles exist, their presence would manifest as missing energy or unexpected deviations in collision data. Additionally, the LHC is used to test theories that predict new particles arising from extra dimensions, such as Kaluza-Klein particles or supersymmetric particles. Detecting these particles would provide strong evidence for the existence of hidden dimensions. The data collected by the LHC is analyzed by international teams of physicists who look for patterns and anomalies that could indicate the influence of hidden dimensions. The findings from these experiments contribute to our understanding of the universe's fundamental structure and the potential existence of extra dimensions. Quantum entanglement, a phenomenon where particles become interconnected and instantaneously affect each other regardless of distance, might also provide insights into hidden dimensions. Entanglement suggests that there could be deep underlying connections in the fabric of reality that we do not fully understand. Some physicists propose that hidden dimensions could play a role in entanglement, providing hidden pathways that allow particles to communicate instantaneously. This idea is speculative but intriguing, as it could help explain how entanglement operates over vast distances without violating the principles of relativity. Research in quantum information and quantum computing also explores entanglement, with experiments designed to test the limits of this phenomenon and its implications for our understanding of space and time. By studying entanglement and its potential connections to hidden dimensions, scientists hope to uncover new principles of physics that could revolutionize our understanding of the universe's fundamental nature. The quest to uncover hidden dimensions is far from over. Future experiments and missions are being planned to probe deeper into this profound mystery. Next-generation particle accelerators, more sensitive gravitational wave detectors, and advanced space telescopes are some of the tools that will drive this exploration forward. New missions such as the James Webb Space Telescope and proposed gravitational wave observatories in space will provide unprecedented data about the cosmos. These instruments will allow scientists to test theories of hidden dimensions with greater precision and explore the universe in ways previously unimaginable. International collaborations and interdisciplinary research will play a crucial role, bringing together physicists, astronomers, mathematicians, and engineers to tackle the challenges of detecting and understanding hidden dimensions. As we push the boundaries of knowledge, the search for hidden dimensions will continue to inspire and challenge us, offering the promise of new discoveries and a deeper understanding of the universe's true nature. The concept of hidden dimensions has profound philosophical implications. It challenges our perception of reality and our understanding of the universe. If extra dimensions exist, they could reshape our notions of space, time, and existence itself. The idea that there are aspects of reality beyond our direct experience invites us to reconsider what we know and how we know it. It suggests that the universe is far more complex and interconnected than our everyday experiences reveal. Moreover, the search for hidden dimensions raises questions about the limits of human knowledge and the nature of scientific inquiry. It exemplifies the spirit of curiosity and the drive to explore the unknown, pushing the boundaries of what we can perceive and understand. Ultimately, the pursuit of hidden dimensions is a testament to the human spirit's unending quest for knowledge. It reminds us that the universe is full of mysteries waiting to be discovered and that our journey of exploration is far from over. We've journeyed far, haven't we? From the familiar three dimensions of our everyday experience to the mind-boggling realm of string theory and the multiverse, the concept of hidden dimensions challenges our perceptions and stretches our imaginations to their limits. We've explored the historical roots of this idea, from the philosophical musings of ancient thinkers to the rigorous mathematical frameworks developed by modern physicists. The search for hidden dimensions is a testament to the power of human curiosity, our relentless drive to understand the universe and our place within it. It's a search driven by both scientific rigor and a sense of wonder, a desire to peer beyond the veil of the familiar and glimpse the true nature of reality. While we haven't conclusively detected these hidden dimensions yet, the evidence continues to mount. Subtle anomalies in particle physics experiments, the strange behavior of gravity at extremely small scales, and the echoes of the early universe imprinted on the cosmic microwave background radiation, all hint at a reality far richer and more complex than we ever imagined. The pursuit of hidden dimensions is intricately linked to one of the grandest challenges in modern physics, the quest for a theory of everything. This elusive theory would unify all the fundamental forces of nature: gravity, electromagnetism, the weak force, and the strong force into a single, elegant framework. String theory, with its requirement for extra dimensions, offers a tantalizing glimpse of what such a theory might look like. By proposing that everything in the universe is made up of tiny, vibrating strings, and that these strings exist in a higher dimensional space-time, string theory attempts to reconcile the seemingly incompatible worlds of quantum mechanics and general relativity. If successful, a theory of everything would not only revolutionize our understanding of the universe, but also open up new avenues for technological advancement. Imagine harnessing the power of extra dimensions for interstellar travel, or tapping into the energy of the quantum vacuum. These are just a few of the possibilities that a deeper understanding of the universe's fundamental laws could unlock. The search for hidden dimensions is not a solitary pursuit. It's a global endeavor bringing together physicists, mathematicians, astronomers, and engineers from all corners of the world. Large-scale collaborations like those at CERN's Large Hadron Collider exemplify the power of international cooperation in pushing the boundaries of human knowledge. As technology advances and our understanding of the universe deepens, we can expect even more innovative experiments and observations designed to test the predictions of string theory and other theories that propose the existence of extra dimensions. Next-generation particle accelerators, more sensitive gravitational wave detectors, and space-based telescopes will provide us with unprecedented views of the cosmos, allowing us to probe the fabric of reality with ever-increasing precision. The journey ahead is full of challenges, but the potential rewards are immense. Each new discovery, each piece of the puzzle we uncover, brings us closer to a more complete and profound understanding of the universe and our place within it. The universe is full of mysteries, hidden wonders waiting to be unveiled. The quest to understand hidden dimensions is a journey into the unknown, a testament to the boundless curiosity and ingenuity of the human spirit. As we continue to explore, we must remain open to new ideas, willing to challenge our assumptions and embrace the unexpected. The universe has a way of surprising us, revealing its secrets in ways we could never have imagined. So let us continue to explore, to question, to dream. Let us embrace the mystery and wonder of the cosmos, for it is in the pursuit of the unknown that we truly discover who we are and what we are capable of achieving. The unseen realm beckons. Are you ready to answer the call? The universe is a vast and mysterious place, and hidden dimensions are just one of the many wonders it holds. If you're as captivated by this topic as I am, then I encourage you to delve deeper, to explore the frontiers of physics and cosmology and unravel the secrets of our universe. Don't let your curiosity end here. Seek out more information, read books and articles, watch documentaries, and engage in discussions with fellow enthusiasts. The more we learn about the universe, the more we realize how much more there is to discover. And who knows, perhaps one day you'll be the one to make a groundbreaking discovery, to unlock the secrets of hidden dimensions, and reshape our understanding of reality itself. But for now, keep questioning, keep exploring, and keep your sense of wonder alive.